Hello, welcome again. We are solving some questions of strength of material. The topic is shear force and bending moment diagram, bending stresses, combined bending and torsion. Question number 40 is consider different sections and variation of shear stress and bending stress across the section. So this is a section and this is bending stress variation, this is shear stress variation. So first section is your scale section, bending stress variation linear and this is parabolic. Okay, and the other one is circular and the variation of stresses are same. And third is I section and variation of stresses are same. And fourth is I section, variation of the bending stress is same but variation of shear stress is different. Okay, so question is which of the following is not correctly matched? Option 1, sorry, option A 1, 2, 3 and 4, option B 4 only, option C 3 only, option D 2 only. So here this is a section and this is your bending. Here the bending stress variation is linear and here the bending stress shear stress variation is parabolic. So bending stress is zero at neutral axis and maximum at extreme fiber. So this is correct. Whereas the shear stress variation is parabolic and the variation of the shear stress is given by this formula, that F A y bar by Z I. So this gives the parabolic variation with maximum at neutral axis and minimum at extreme fiber. So this is 1 is correct. Similarly 2 is also correct, but 3 is not correct because here the formula is F A y bar Z by I. Okay, so Z varies suddenly from the bottom of the flange to the top of web. So there is no sudden variation in shear stress corresponding to that variation. So that corresponding to that variation, this 4 is correct. So 3 is not correct. So answer is option C. Okay. So answer is option C. Next, consider the I section, point P and Q in I section are shown near the junction of the web and flange. The point P is on flange and point Q is on web. The ratio of shear stresses on these 2 points will be. So this is your 100 mm, this is 10 mm, this is P, this is Q, this is 80. This is your 8, this is your 80 and this is your 10, this is 10, this is 100. So options are A is equal to 5, B is equal to 10, C is equal to 8, D is equal to 5 by 2. So this is the, so the shear stress variation is given by F A y bar Z I, Z by Z I. So at the top of the at the bottom of the plane, the point, suppose there is point P and the width of that section is 100 mm, and at the top of that, suppose point is Q and width is 10 mm. Okay, so the ratio of shear stress is ZQ by ZP is equal to 10 by 100 or 1 by 10. So tau Q by tau P is your 10. Okay, so the ratio of shear stress is option B. Next, if a beam of rectangular cross section is subjected to a vertical shear force V, the shear force carried by the upper 1/3 of cross section is option A 0, option B 7, B by 27, option C 8, B by 27, option D B by 3. Okay, so suppose this is your beam, okay, and this is the neutral axis or central axis. This is the distance. This is a section of depth D by 3. This is B, and if it is D by 3, then it is D by 6, and this is D by 2. Okay, and the shear stress is given as B A y bar I B. So B is your shear force. A is the area above the section considered. Y bar is the center of the section, so distance of the center of this section to neutral axis. I is moment of inertia and B is weight. Okay, suppose we take a section at a distance y, then this will be your d by This will be total is d by 2, so this will be d by 2 by minus 5. Okay, so this width will be d by 2 minus 5, and sorry, this depth will be d by 2 minus 5, and this width is b. So the area is d by 2 minus 5 into b. Okay, and now this y, now we have to determine the y bar. We have determined a, we will determine y bar. So y bar is y plus distance of center of this section from this bottom. So d by 2 d by 2 d by 2 minus y, because this is your d by 2 minus 5, and if we divide by 2, then it is d by 2 minus y by 2, and this is y, so y plus d by 2 minus y by 2. Okay, so this is the your y bar, and this is I is moment of inertia of all section, b is width of all section. Okay, so b will cancel out, and if we solve this, we get v d square minus 4 minus y square 2y. So this is the shear stress variation. Okay, so now the shear stress, from the shear stress, this is the shear stress at a section uh, at a distance y in of thickness dy. Okay, so df is tau, sorry, this is the shear stress at a section at a distance y in a section dy. Okay, so the shear force, small, if we multiply it by small area, this shear stress, then we get the small shear force, that will be tau into b into dy. Okay, so this is tau, and b into dy is the area of that section. Okay, so if we multiply it, then it is a small force. And now if we have if we want to calculate the force carried by this portion, we will integrate it within the limit. So this limit is from this limit is d by 2, and this limit is d by 6. So d by 2 to d by 6, v 2i d square minus 4 minus y square dy. Okay, so v by 2i d by 2 minus d by 6 d square by 4 minus y square dy. So if we integrate it, d square by 4 into y minus y cube by 3. Okay, and limits are d by 2 to d by 6. So putting these values, we can get and solving this, putting this limit and solving this, we can get 7v by 27. So answer is option B. Okay, so answer to this question is option B, 7v by 27.